All right, so the formula is E is negative 13.6 over n squared, and then they enigmatically put the units electron volts to the side, right? Now we're going from 2 to 7, right? So we're going from a more tightly bound to less tightly bound. We're increasing the energy of this electron, right? So therefore it requires an input of energy, so therefore the electron is being absorbed, right? So absorbed kicks the electron up. Emitted is when it goes down closer to the atom and gives off energy, right? So let's figure this out, right? The initial energy state is negative 13.6 over 2 squared electron volts, right? And this 13.6 is made up of all kinds of stuff, like the Z of the atom, the electron charge is built into that, right? You should look in the book because he derives, Jean Coley derives this actually. Okay, but for my part, I'm just simply going to use negative 13.6 divided by 2 squared, and that's negative 3.4 electron volts, and the final energy is minus 13.6 over 7 squared. 6 divided by 7 squared is negative 0.27755 electron volts, right? Okay, and then the change in energy of the electron is, of course, final minus initial. So I'm going to go that guy minus the negative 3.4. And I get that the change in energy of the electron is positive 3.122 electron volts, right? So since it's a positive increase of energy of the electron, it took a photon to do this, right? How did it gain that energy? Well, it got it from the photon, right? A photon with precisely that energy came in. There you go, right? Okay. So now we got to figure out what the wavelength of this thing is, right? And we get, I believe we've got a formula that says wavelength is hc over energy, right? And of course we'll have to multiply that by 1.602 times 10 to the minus 19th, and this is joules per electron volt, right? And plug that in here, right? So the wavelength is 6.626 divided by 3.122 electron volts, and then of course I'm going to here we go. Okay, so 6.626 E minus 34 times 3, 8 divided by that answer that I just got divided by 1.602. And I get 3.973 times 10 to the minus 7th meters, which would be 3.973. Right, I could move this over and go 397.3 times 10 to the minus 9th, and then that would be nanometers, right? It's fine to just leave it like this, okay? Now, hold on to this notion of 3.122 electron volts. I'm going to show you a shortcut that you can do it's in the data packet, it's in the front section here. Let me just show you this. Okay, let's find it. All right, let's just go up to the front. Here we go. Notice that they give HC in terms of joule meters and in terms of electron volt meters, right? Okay, so let's go back. 1.24 times 10 to the minus 6th, right? Okay, so we ended up with 3.1224 was the next number, right? Electron volts. And then we wanted to find the wavelength. So wavelength is HC over E, right? So I'm going to use 1.24 times 10 to the minus 6. I just saw that in the data packet, right? And this is electron volt meters. And then divide by. So if I take that 1.24 e minus 6 divided by, and then I'm just going to get that answer, the 3.122. I get almost the same number, right? 3.971 in this case, times 10 to the minus 7th meters, right? Which is the same thing we just got. This is just a little bit shorter. We don't have to type. Basically, that 1.24 times 10 to the minus 6 electron volt meters is hc over little e, the electron charge.